Good afternoon, everyone. Appreciate y'all coming by, sitting into this presentation. We're going to be going over Energy Advantage Program, which is an offering from Flowserve. My name is Tyler Thomas. I'm one of the engineers in the Energy Advantage Program. My background is systems analysis and vibration analysis. Been doing systems type analysis on rotating equipment and fluid moving systems for just about 11 years now. Based out of Houston, but generally service a global region. We also have a global team. So this is really reducing greenhouse gas emissions through energy optimization of pumping loops was really how this was coined. So a little bit of backdrop on Flowserve and why it's important to talk about Flowserve and how it relates to systems optimization and how we go about optimizing systems. So Flowserve is a world-leading manufacturer and aftermarket service provider. There's really three key categories that we have offerings in, and that's pumps, valves, of course there's mechanical seals, and then we have a very robust aftermarket services and solutions group that kind of leverages upgrades, modifications to pumping systems, and things like that. So an overview of the Energy Advantage Program. So we are a analytical team that is very data-driven in our work process with a goal of increasing energy efficiency through optimizing flow loops. How that looks and what our key takeaways of that are is reducing carbon emissions, reducing greenhouse gas emissions, increasing overall efficiency of flow loops. Baked into that is the reliability aspect of those flow loops. When we're looking at optimizing those flow loops, we're also going to be looking at how it can make any reliability increases, increase mean time between failures, and increase throughput and uptime. So industry challenge. This is really the why we exist, right? So there's four main pillars that have really existed throughout industry as far back as you can go in really looking at heavy industry. Safety is always kind of a key paramount part of that, right? We want a safe working environment. We want to limit the amount of injuries and, of course, fatalities. Output, how are we increasing plant uptime and output? Plants want uptime and output. That's what one of their main drivers are. And, of course, reliability, increasing plant mean time between failure. This is tied into keeping assets moving, keeping throughput and output where it should be, and of course quality. You're delivering a product to an end user, whether that be to another industry or whether that be straight to the end users. Now, one thing that has come to be a fifth pillar, if you will, is sustainability. If you look at any company, Flowserve included, and whether it's heavy industry, chem, petrochem, oil and gas, even pulp and paper, power, everybody has ESG goals and sustainability goals that they're looking to hit. So where we can fit into that is generally the large type projects that are meant to make those sustainability goals focus around things that are highly engineered, very high lead time, projects that span multiple years and are quite expensive. They do have good success, and there is reduction in emissions and greenhouse gases and things like that for those projects. Those do exist. They are not very fast to market. Where Flowserve has seen that we can fit in is a very fast to market type approach to cost decreases, operational cost decreases, greenhouse gas emission reductions, and overall optimization and efficiency quite quickly, right? And these exist in really when it comes down to it in upgrades to the system that will optimize them in terms of pressure reduction, flow reduction, increase in efficiency, and all that'll really make sense once I get down into what our methodology is. So we really have a three-step approach. This is the how of what we do, right? So step one is to analyze those systems. We want to take almost a plant-wide and by and large, we look at multiple loops. And when I say loops, I mean multiple flow systems, whether those be in multiple units or all in one unit. The drive there is to look at multiple pumps, not just a single pump, right? The step 2 in that is to create a tailored recommendation to that. We are going to analyze that system. We're going to figure out what drives the system, what the new conditions of service are, and then make a recommendation to match those new conditions of service that we have set. Step 3 to that is an implementation. So that looks, and you'll see kind of what those implementations look like by and large. I have a few case studies on the back end of this. Those look like upgrades to the system, upgrades to specifically the rotating equipment, the pump, maybe to the valve as well. We look at all of those things. So common optimization opportunities. This is the what. This is what we really are focusing on during our analysis. So it may be design influences, or sorry, design inefficiencies, conservatism in initial design. So we find this a lot, right? So whenever plants were designed and built, maybe in the 60s, 70s, 80s, when a lot of heavy industry was coming about, new refineries were being built, petrochem was being built, energy in itself was very cheap and not really a driver in how we design or how EPCs design those systems, right? So let's say an end user needs a flow loop at 1,000 gallons per minute and 1,000 feet ahead, right? They go to an EPC and say, this is what we need. The EPC reaches out to somebody like Flowserve and pumps and says, hey, this is what we need, 1,000 gallons per minute, 1,000 feet. We're not gonna design a pump specifically just for that, right? There's gonna be some conservatism in it. We don't want to just give you 1,000 gallons a minute at 1,000 feet. So if you have any types of degradation in that loop, it's not gonna be able to maintain that output, right? So there is some conservatism that happens. It's a design creep, right? And it's inherent in design. We see it on a daily basis when we're doing analysis on these flow loops. The same thing happens with the valves. Similar thing. You know, they go out and spec out a pump, and they go out and spec out a valve. Both of those will have some conservatism. That valve isn't going to be running at 90% at that rated point. That's not how valves are spec'd out. They're going to have some conservatism. They're going to be a bit oversized. How much they're oversized, that's what we're out there to find, right? So operational inefficiencies, excess pressure generation. I'll really drill down into these categories. Unnecessary recirculation. Operating away from best efficiency point, or BEP. These are all things that we look at in the analysis. Mismatched components. Look at maintenance-related inefficiencies. Degradation to the equipment. So a pump that has been operating for 10, 15 years, right? If it hasn't been reworked or something like that, there's some degradation in that system. What can we do to fix that? These are all things that are provided in an all-up recommendation that isn't just a recommendation based on flow, isn't just a recommendation based on pressure, but a recommendation based on optimizing the system in all aspects that we can touch, right? And then, obsolete or inefficient motor technologies. Old plants, and really when you start getting into oversized equipment, you can have, IE2, maybe IE3 type motors that are a little less efficient than our current IE5 or super efficient motors that are out there. This is compounded if these pumps are way oversized and maybe operating at 25% BEP. I have a really good case study on a system that is just that. If it's operating at 25% BEP, that pump that motor is not loaded. The power factor of that motor is down. The efficiency is down. So we can provide in our recommendation, like I was kind of talking about, an all-up round in terms of optimization to do everything to create the most efficient asset that we can. So let's take a look at commercial risk. Life cycle costs for a pumping system. So about 40% of the overall life cycle cost for your typical pump is in energy. That is the energy cost associated to put the work into the motor and turn the pump, right? About 25% of that is in maintenance on average. The pump purchase itself is really only about 10%. It's a very small number in terms of the grand scheme of things for a life cycle of a pump. About 10% in operation, 7% installation, 5% in environmental, downtime at about 3%. That cost can vary greatly, and I think anybody who has seen any kind of operation in a plant knows that. if a flow loop goes down, especially if it's a critical service, the unit goes down. If the unit goes down, you are losing money. There is cost associated with that. Many times it's millions of dollars a day, can be very detrimental. So how do we go about attacking this, right? So if you look at the average annual operating cost, that is brake horsepower, times operating hours times electricity cost. Operating hours we're not really going to be able to change, right? By and large, when you look at a flow loop that's operating, it's operating at a specific number of hours per year on average, and that really doesn't change year to year. We're not talking about outages that can change things, just annual operation hours. Electricity costs, those do vary, and they have varied and continue to vary, right? They're not going down. They're always increasing, depending on where you're at, increasing more or less, but they are increasing, period. So boil that down to what we can control from a flow loop and how we can optimize the brake horsepower consumption, right? So general calculation for brake horsepower. Q is flow. TDH, total differential head, that is pressure, specific gravity on the numerator. On the denominator, we have pump efficiency and motor efficiency. What can we change in that? We can change flow to an extent, and I'll get into this here in a minute. I'm never gonna change downstream flow in the system, right? If we're talking about a system in general, a pump, a valve, pumping into something. The downstream pressure and flow, downstream of that valve, we're not gonna change. That is what the system needs, not looking at changing that. When we're looking at flow, we're talking about recirculation that's happening. Are the pumps a bit oversized and you're recirculating back to the suction source or back to a flash tower or something in order to push the pump out on the curve? Or maybe recirculating in order to push the pump out on the curve to decrease pressure because you're protecting some fixed equipment in the system from overpressurization. We see these things, they exist. TDH, we can change that, right? If we look at a valve, there is an upstream pressure and there is a downstream pressure. The pressure being broken down across that valve, specifically at max flow rates, where the differential pressure is at its least, where the valve is open at its most, is what we're really keying in on and designing to. If there's a large pressure drop at that max flow rate, we can bring that upstream pressure and downstream pressure together. Again, we're not changing the downstream pressure. It's going to look like changing the upstream pressure. That looks like a decrease in pressure that the pump is producing. That'll all make sense here in a minute. I'll really get more into that. But specific gravity generally can't change, right? Maybe the specific gravity has changed throughout the years. If your amine system has changed just a little bit, and so now there's a different specific gravity there, or crude production has changed. Maybe you were doing real heavy sours, and now it's changed, and so you're doing a bit different. There's a different specific gravity. That changes the hydraulics of the pump. We can take a look at that as well. Pump efficiency, we always try and create or put a pump or make a recommendation that makes the most efficient pump as we can. We get our hands tied behind our backs in some senses sometimes. There are just some really hard services based on the condition of service to put a pump in. But we try our hardest to give the most efficiency that we can. If we can increase efficiency, again, all of this boils down to decreasing that brake horsepower consumption number. You decrease the brake horsepower consumption, you decrease energy costs associated with operating, you decrease greenhouse gas emissions associated with Scope 1 or Scope 2 emissions that you are using to create power, or that is being created for you. Motor efficiency, I already got into that. If we're sitting, if there's a flow loop that has old IE1, IE2, maybe IE3 that are generally less efficient as you unload the motor, we can look at right-sizing the motor to load it properly, maybe an IE5 or super efficient motor accompanied with that upgrade in order to, again, create a complete optimization upgrade. So let's get into the model development. And this is really like the bread and butter of what we do, how we do things. General pump upgrades in the past, re-rates have existed just at the pump, right? So, the end user comes to us and says, again, we need this flow, it was this, we need this flow. Well, the thing to ask there is why? Why do you need that flow? Why do you need that pressure? What changed? That will create some conversation that may put you into a corner, it may not. But what we're gonna do is not start with the pump, right? If we wanna optimize the system, we need to understand what is needed on the downstream side of the system. This sets the conditions of service. So if you look at the valve here, we have an upstream pressure, we have a downstream pressure, and we have a flow transmitter. So the FT flow transmitter, that'll be the total flow into the valve. We have pressure transmitter, upstream, downstream, that gives us pressure, and generally we'll have valve position through a flow controller, right? It is looking at either a flow controller or a pressure controller. Maybe it's a level controller. I guess the overall synopsis is that we have valve position. If we have pressure transmitter, flow transmitter, valve position, we can create this graph, which is really, really quite helpful. So this is about 3 years of data at 1 hour intervals. It's a lot of data. We've created some internal proprietary type tooling and modeling software to look at valve operation. So if you look at the blue plot here, that's the downstream pressure versus flow. This sets the conditions of service. If you remember what I was talking about, looking at max flow rates where the pressure drop across the valve is gonna be at its least, this is what I'm talking about. We need to understand what's happening here and design to it. So hard to tell color, but the top scatter is orange. Forget about the green scatter for a minute. That top scatter is gonna be the upstream pressure and flow that is going into the valve. That difference is you can really call that difference at max flow rate the ability to reduce costs associated with pressure production in the system, right? If we can now take into account the green scatter, that's reducing pressure to an agreed upon margin with our end user. So we have a discussion when we start getting to this model development in the analysis. And I'll go over kind of what that looks like here in a minute. But there's a conditions of service call where we'll say, hey, this is what we're seeing. We saw 3 years worth of data. We're looking at your downstream valve. Let's say you have 100 PSI of pressure drop at those max flow rates. We talk with them around their standards. Maybe your standard is we require 40 PSI at max flow rates at all times at least. And so we can reduce the pressure in our model to maintain a 40 PSI, in this instance, 40 PSI margin at max flow rates. So we have a reduction in pressure. So that's step one. We've just done the first step in optimizing the system of excess energy. In that same step, we're looking at the control valve CV and looking at the controllability. If you have a control valve, maintain flow, reduce pressure, upstream pressure, your valve is going to open up. There's just the fundamentals of physics there. When that opens up, are we maintaining controllability in the valve? If we keep opening it to those max flow rates, do we keep increasing flow, or does it flatten off? If it flattens off, we have a problem. Either we have choked flow, or we've got to the point where our maximum flow rates, the pressure versus flow, are either touching or crossing. We get to that point, you don't maintain in controllability. This is such a crucial step. This is such a crucial point in that step, and we spend a lot of time in the analysis looking at this interaction. The model, the tooling software that we've created really, really revolves around this type of calculation. Working our way back now, right? Remember, away from the pump, looking at the valve, and then working our way back, looking at flow. Is there recirculation, and why is this recirculation happening? I kind of mentioned a couple of these, but are you recirculating because the pump is oversized and you're pushing it out on BEP? Maybe you're reducing pressure by pushing it out on its curve, which will maybe protect some fixed equipment that you have. Whatever the case, why are you doing this? Can we reduce it? If we can do those two things, we can then, wrong way. We can work our way back to new conditions of service. If we find new conditions of service, we can look at what upgrade fits in there. So maybe that upgrade is a trim. Maybe it's a donor hydraulic or a low flow hydraulic. Maybe it's an engineered drop-in pump. It can look like a lot of things, but what it isn't is like some magic upgrade that hasn't existed in the past, right? These upgrades are normal pump upgrades that Flowserve and Qualitech have done for years and years and years, right? So it's not magic, but it's how we get to those new conditions of service that is kind of the new tactic on upgrading these systems or looking at optimizing these systems. This is where we go and try and tweak efficiencies. So we've designed to a flow and pressure. Brake horsepower consumption, remember, flow, pressure, not changing specific gravity. When we get here, I can start looking at efficiency. Where's the pump operating at? Is it operating back on the curve? Is there something we can do to, to make an upgrade that hydraulically fits the pump to the system? That's the big question. You can start making efficiency increases on the pump there. You can start making efficiency increases on the motor there under certain situations, right? Optimizing drivetrains. So is there an ability to implement a VFD? I talked about super efficiency motors. There are lots of instances, and I really like looking at systems that already have VFDs in them, because by and large people think, oh man, it's got a VFD in it. It's probably going to be a pretty efficient system. And it's not always efficient. There's a lot of times where you walk up to a system and it's operated on VFD, and maybe they're controlling speed, but they're also controlling 6 parallel valves that are all going into a furnace. So they're controlling on speed and controlling on valve position. Those two things are fighting one another. And it's an unoptimized system, right? And so the recommendation may not even be a pump upgrade. It may just be, hey, open your valves up and control on speed. By the way, here's your targets based on output. So the implementation cost is engineering hours or maybe operation hours on their end, but it's not a change to the equipment. While I'm not a salesman. I'll take off my sales hat and throw it. Whenever I start doing these projects, I'm a tool for the end user. I'm a tool for you, right? So how can I make your system as efficient as possible at the lowest cost to you? Like my whole analysis is driven on ROI and IRR. I want a really low ROI. I want a really high IRR for you guys. If I can do that through optimizing a VFD on speed, awesome. Like that's a win-win for everybody, right? Valve modifications. We are able to leverage the expertise that Flowserve has in having pumps and valves to bring those two together and unsilo them, bringing those two divisions together to work together to create these recommendations. And whether that looks like, completely changing out a valve, or maybe just recommending a new trim specification in a valve. We often look at that. So measurement and verification. I mentioned that we are leveraging installed instrumentation most of the time. This is because it's a really hard thing to do. If there's an uninstrumented system, it's a really hard thing to do to go completely instrument it. It's a heavy lift, right? Are there straight runs of pipes that we can use ultrasonics? Is it too hot where we can't even use ultrasonics? If it's north of 400 degrees, it's real hard to take measurements in flow. You can do it through some ultrasonic flow meters. I've done it through just the worst. It's just real hard to do. I'll just leave it at that. I won't get into it. But if we leverage that installed instrumentation, we can create that baseline power consumption. We make the recommendation. That becomes the projected power determination. So this is what you had, this is what we think you can have based on the recommendation. After execution, then we can then come back and do a post-optimization power validation. It's a lot of words, but it's just really an apples-to-apples comparison, right? If you have instrumentation and I pulled that instrumentation and those data tags in order to do the analysis, I can turn around after execution, let it run, start up, and get to normal operation, and pull those same data tags and look at it apples to apples and see the step change in pressure, see the step change in flow reduction, and actually quantify the post-execution brake horsepower consumption to the recommended. And that's not just looking at brake horsepower. I mean, did we hit the numbers we were thinking on brake horsepower consumption, which trickles down into greenhouse gas emission reduction? Are we hitting our targets, right? So the assessment process. By and large, this is really geared as not just a single pump that we're going to go look at. We really like to look at these things in in a number of flow loops at a time. And that can happen for a number of reasons. Sometimes flow loops are all tied together in one way or another. Maybe they're booster pumps pushing into main pumps, things like that. But the first step in all of this is collecting asset information. I need to know the asset list that you have, and a lot of times that looks like a motor install list or something like that. We can tell a lot from the motor install list. Service, brake horsepower, all of those things. Then we do a candidacy review. If we have that install list, we're going to boil that down into systems that we know that we can work with. Generally, in this type of analysis, we're looking at higher horsepower type assets, right? So the higher horsepower assets, which are really the critical assets in the system, those are they're using the most energy. Generally, they're pretty well instrumented. Generally, I mean, we'll put a huge asterisk by that, right? It kind of depends, but most of the time, 5 horsepower pumps, 15 horsepower pumps, not hugely instrumented because they're just not critical systems. Now, some of those may be critical systems, and we can look at those in a certain aspect. But by and large, we're looking at higher horsepower stuff. So the candidacy review is the ability for me to say, hey, here's the pumps I want to look at. And then you to say, okay, I think this one, add your notes in. This one, we used to run it, 1 out of 2. Now we're doing 2 out of 2. Or this one, man, we're throwing seals at this. Our mean time between failure is 6 months. Like, we need some help with this. So we get all of that information, boil it down into a targeted pump loop list, right? After that, there's a P&ID review. This is something that we work with you to gather P&IDs, and that's through either coming on site and collecting those. We've partnered with end users who give us access to their systems to be able to pull drawings, pump drawings, valve drawings, P&ID drawings. There's contracts that we have in place that protect both companies in doing that. We're very well versed in doing that. So this P&ID review, we are, for an asset, for a flow loop, I'm pulling all the P&IDs. We're tracing it from suction source through the pump, through the valve, through the end user. This is really what I'm trying to get to, right? Like, I need this. I need to be able to draw a PFD and understand what instrumentation is there. If I can understand what instrumentation is there, I can understand if we can analyze that system, or if we need to fill in some gaps, right? Flowserve has the ability and has teams such as our solutions engineering team that is tooled to go out and collect flow data, tooled to go collect vibration data, pressure data. We have that ability. We also have some of our IoT stuff like Red Raven, where we can go and install instrumentation that can collect and give you access to it as well. But P&ID review gets us to the next step of the feasibility review or feasibility analysis. That's where we're saying, hey, we started with 15. That was our goal. We did the P&ID review. 5 of these are going to fall out either due to overcomplexity, non-instrumentations, or something like that. The overcomplexity part, there's only so far you can go before you have to start getting into some really difficult modeling analysis with things like AFT Fathom, maybe something like that. Those are really, really huge lifts to get to those. So we start having some conversation around if we want to go down that path or if that wants to fall out, right? System analysis and modeling, I really went through that already. The conditions of service review, I discussed that. We'll get into it a little bit, kind of what and who is involved in those conversations there. Then we get to solution development and report. Each one of these loops is going to have an individual loop report associated with it. So think of like a seal change out recommendation, right? If you're having trouble with a seal, generally, you'll say, hey, I'm having trouble with this seal. What can we do? A recommendation is built out specific for that flow loop, specific for that asset. That goes into a project funnel, goes through its approval process, stamps of approval, all these things. That's really what this is geared like. There's an individual loop recommendation, so not an 80-page, 90-page report that is really hard to read and understand. It's very boiled down. This is what we found. This is the analysis. This is the recommendation. This is the economics behind it. So, I mean, these are like 10-page reports, and like a couple of those pages are title pages and abstract, or not abstracts, table of contents. So really easy to digest, really easy to move through your project funnels. And then final review with the site. So we provide that report, and then there's another touch point where we want to go over that report with the stakeholders, reliability engineers, operations engineers, those types of things. Any questions to this point? And if there are questions, don't hesitate to stop me and ask those. We can be as informal as we want to be here, I think, which would be helpful. So the process, I've kind of described each one of these: data gathering, analysis, conditions of service, recommendation, and report. There's some dwell times in each one of these. Even if you're doing, 15 to 30 different loops. I'm working on a project right now where we're looking at 30 different flow loops in a facility. The project time frame for that, for those 30 loops, each one of them having a recommendation, whether that recommendation, each one of those having an output, whether that is a recommendation or whether that output is, hey, you're doing really well on this flow loop. Like, I'm not going to try and peddle some optimization that doesn't make sense for anybody, right? So the general project timeline is 3 months. We maintain that. So it's generally pretty quick in the grand scheme of things. This can be shorter, it can get shorter, or it can maintain. There's a lot of things that depend upon that, and that's access to information, things like that. If I got to travel on site multiple times to pull data or multiple times to pull P&IDs, there can be some prolonged time in that first 1 month period. But after that, once you get to the analysis, the end user is hands off. This is all me and my team, right? We're doing all this analysis. We're setting up condition service calls with you, and those are like hour-long, maybe an hour-long meeting where we get on Teams or maybe come on site and present it to stakeholders. Recommendation and report. All of that is within my team. It's taking the burden off of the end user, being very respectful for your time. You have things to do that don't involve this, right? So, acceptance criteria. These are pretty important things that if you're thinking about doing that you really need to wrap your head around, because they're going to be some of the first questions that we need to know. What minimum IRR percentages do you look at for project funnel approvals, right? What's the max ROI that you have the ability to really even call it a project worthwhile putting in your project funnel? What are energy prices in dollars per kilowatt hour, dollars per megawatt hour? What are CO2 costs? What is the cost associated with greenhouse gases, with CO2 gases? And then CO2 intensity, it can be given in a few different things. Generally, we have here pounds per megawatt hour. So the conditions of service call, I wanted to spend a little bit of time here because it's such an important thing in the process, and is really the heaviest lift in terms of time constraint for the end user, right? So this is a condition of service call. It takes place right in the middle, right after the analysis, before the recommendation phase, right? So the purpose of this call is to discuss the loops that we're doing analysis on, sharing preliminary findings. So, hey, we found this is how this is operating. Does that make sense? Does this look correct to you? We made these assumptions. What do those assumptions mean to you? Can we move forward with them? It's a validation phase that's super important, and if skipped, it's kind of detrimental to the project, because then you start blindsiding people with recommendations that they're not really aware of why we're doing it, right? So this brings it into the purview of the unit engineers, into the purview of the operation engineers, who are really, day to day on the ground working these assets, right? And I think I kind of already talked about the typical question topics, discussions around reliability, if there's any issues that you're having with them. This is where discussions around mean time between failure, or maybe seal failures or things like that start coming into play. Operation philosophies, fouling and fixed equipment, things like that. So in that whole discussion around the pressure differential across the valves, that margin that we're maintaining, a lot of that conversation comes from, hey, is there fixed equipment in this loop? Maybe it's a bottoms loop that is real heavy. Exchangers foul quite a bit. We want to maintain more margin, so those kind of discussions come out of these calls. Very important. Potential candidates. So these are really the loops that when we start defining an asset list, the good ones to include in that list, right? So any existing re-rates, again, why are you re-rating that? Is there something that we can look at to piggyback on that re-rate to help you pay for it in terms of an ROI or IRR perspective? Loops where valves are operating below 50%. If it's operating below 50%, generally speaking, there's some pressure being lost or broken down across that valve, right? Those are great opportunities to look at. Process units that are known to be oversized or have D-rates. Old process loops where conditions of service have changed. Low pressure ultimate users, maybe it's pushing into a vac tower or a flash column or something like that. We know that that downstream pressure is pretty low in terms of needs, right? So what can we do to optimize that, right? There's always, I'm not gonna say always, a lot of times there's a pressure reduction that can be had there. Pumps with VFDs, or just used for slow rolling or soft starts. I kind of already talked about that. I won't dwell into it anymore. So I'm about to get into case studies. Over what I've talked about so far, the process, the model development, what we do, what we're about, why we're about what we're about. Any questions on that at all? Okay. So I have a few, I think I have 3 case studies here. These are real-world case studies, things that I myself have done in terms of projects. So this is a case study on a lean amine pump system, really revolving around recirculation and overpressure in the system. The interesting thing about this one is you've probably heard me like drum that we look at the valve, we look at the valve, we look at the valve. There's not a valve in this system other than the flash. Man, it's kind of grainy, isn't it? Kind of hard to see that, yeah? Yeah. There's not a valve in this system if you look at it going to its end users. Let me do this. This will be better. Yeah, there we go. Okay, so there's really no valves in between our pumps here going through the system of exchangers and airframe coolers to 3 different unit of downstream pumps. There is a recirculation back to a flash drum. This is important, very important, and is the reason why we even did this analysis. The pressure reduction on the backside was just a cherry on the top. So the end user is operating these and recirculating some of the flow back to this flash drum. The reason for that was they were overpressuring the system and they needed to protect their exchangers. They were pushing up to the maximum allowable working pressure. If you open up recirc, you're going to push the pump out on the curve. Increase flow, decrease pressure, right? If you look at just generally what a curve looks like. So they needed about 305 PSIG at the lowest end user requirement. So we went and did a field survey for what we were pushing to these downstream systems. It's really hard to see, but this where my laser pointer is a pressure transmitter. So we understood the pressure drop across the system. We have pressure here on the upstream of all of this fixed equipment. We have pressure here on the downstream. We also have flow up and downstream of the recirculation. So we needed 305 downstream. We were delivering about 405. So there's 100 PSIG of excess pressure in that system. Approximately 15 PSIG across the system. We knew that because of the instrumentation. So there's about 70 PSIG of loss across the system that we could do. So pretty small operating envelope on these pumps if you look at where these are plotting at. There's a little bit of degradation, but again, you can see the relation of flow versus pressure, increased flow, decreased pressure, right? They're operating close to BEP, about 90%. It's a little bit of degradation, like I mentioned. So if we look at the recirculation that's happening in this system, the top plot here would be the total flow in the system. Pink would be the forward flow in the system. So that's what we're delivering downstream to the units. Green will be the recirculation. So, you know, it's hovering anywhere between 10 to 30% spillback. This is important and super costly to the end user. This is an amine system. It's a lean amine system. They're recirculating back to a rich amine flash drum. In order to get those amines back into their lean form, there's a lot of 50-pound steam that's being consumed in order to reprocess those amines back. That 50-pound steam has a pretty decent cost associated with it. When they brought this to me, they were like, "Hey, we think we're spending about $600,000 a year in 50-pound steam consumption just to recondition these amines, but we want somebody else to take a look at it. This is the cost we put on steam, so we get that from the end user. It's some of those conditions of service call type things that are really important. So what we did here was understand, again, kind of really hard to see, the flow that we needed in the system, the steam in pounds per hour associated with, and we have steam consumption. We're able to calculate that. So we're able to calculate a steam per flow in pounds per hour. If we know that steam per flow in pounds per hour, we can calculate an average cost associated with each pound of steam consumed, right? If we can do that, we came, boiling that down into about $470,000 a year in steam consumption just based on recirculating. So if we can remove that recirculation, we can save just around $470,000 a year. The big part is, where does that steam go, right? If you save steam but then just vent it to atmosphere, that's not saving steam. There's a steam balance that is associated with the unit that has to take place. We look at that, we talk with the engineers behind that. So, recommendation here. It's just a trim to that pump is all it would require. It maintains 1 out of 2 operation, reduces recirculation, it removes it permanently, to be frank. Maintains high efficiency in the pump, so as there's losses associated with trimming to min trim, but they're pretty minimal, right? We can do some things to combat that. Again, we can do like a blunting or maybe an underfile to lift up efficiency a little bit. So maintains high efficiency. Again, simple trim to the impeller. $539,000 in annual cost savings. So there's about $85,000 in electrical, about $460,000 associated with steam. 195% 20-year IRR associated with this. The site did this themselves in their shop while the unit was online, pulled one pump, trimmed it, put it back in service, started it up, pulled the next pump, trimmed it, put it back in service. This is the field verification that I'm talking about. So the reported savings was about 193 horsepower, about 28%. You can see the steep drop from recommendation or from implementation, execution, to when they started that pump back up. Really hard to see here, but we waited until the system got back up to normal operation to quantify the reduction in flow, right? So validated savings was 204 horsepower, 29%. Pretty dang close. Really pumped about this. End user, super pumped about this. This was almost immediate implementation. Like, they are saving $500,000 annually right now. They did this almost 7 months ago. So they're coming up to coming up to an annual savings on that. So really good recommendation. They're super pumped about this one. As are we. It was a good one. It was fun. So this one here, this is some reactor charge pumps. This is looking at valve throttling and parallel operation. End user brought this one to us. These are critical pumps. These are 1,500 horsepower BB3 style pumps, 2 out of 2 operation. There is no redundancy in the system. If they lose one of these pumps, they lose production in the unit. If they lose production in the unit, it is millions of dollars a day, or sorry, $1 million of loss associated with it. There are two parallel branches, if you can see here, a main branch and then a temperature control branch, and then a main branch and a temperature control branch. Each one of these go through different feeds into the furnace and then into 2 reactors. It is a very well instrumented flow loop. We have total flow through the valves. We have pressure on top of the reactors, so we are able to pull data sheets on the furnaces, pull data sheets on the exchangers, and understand what those pressure drops are across the system. Super important in figuring out what margin we need to maintain at those max flow rates, maintain controllability, right? There was a bypass line back to suction. We don't have we did not have, that valve was generally closed. Like I said, these were Flowserve Heritage pumps, 6x10, 11-stage MSDNs. These are BB3 style pumps. So, starting with the valves, this one is like quintessential what we do, right? Starting with the valves, about 130 PSI through differential at max flow rates through one of our main lines, about 140 PSIG differential through our other main line. The two temperature control lines, about 160 PSI, 180 PSI. So we have a lowest common kind of denominator that you deal with here. So we're really designing to this 130 PSI drop across that loop. That's where we're having to maintain. Data was forced on the curve. We didn't have discharge pressure in this. We made an assumption. We check that assumption out with them at the conditions of service call. If we don't have a discharge pressure, it's really easy to calculate. If we know suction pressure, we know total flow, you can create a perfect fit line on the OEM curve. For every flow, you calculate a TDH, take suction pressure out of that, and you have discharge pressure. Super easy to do. The assumption there is that it's operating on the curve. It is a pretty decent assumption. Like, I've tested, I don't know, probably thousands of pumps now, and many times they're not operating on the curve, even if they're brand new. Like, there's API specifications governing how those are tested, but that's another discussion. We check that assumption with them. They get comfortable with that assumption, and we move forward. The kind of apple-apple comparison here is, if it's operating on the curve, the recommendation that we're going to make, we're going to assume is operating on the curve. If we're going to deliver a pump, it should be operating on the curve when we deliver it, right? So they operated in parallel for the added pressure needed. When you really looked at this asset or this loop, the pressure that they needed kind of fell right in between single pump operation and parallel pump operation. From a flow perspective, the single pump could basically do it. Maybe you'd need to extend the curve out a little bit. There's some ways that we can mess with that, but we needed a little bit more pressure. Generally speaking, there's about 70% efficient in parallel operation. It's operating back on the curve in terms of parallel. So that correlates to operating back on the curve when they're sharing that flow. So about 70% in efficiency. If we get them to a single pump, we can get them to about 80% efficiency. So there's about a 10-point in efficiency increase that we can make there. So what's the recommendation look like? We take that BB3 style pump and we create a engineered drop-in DMX BB3 style pump. This doesn't change, it drops right in. No changes to bolt hole locations, no changes to flange locations, everything bolts right up. Moves to 1 out of 2 operation, gives them a complete spare for redundancy. If they have a seal failure, the other one starts up and they don't have a loss of production event there. High efficiency at average and max rates. I already kind of mentioned there's no civil work associated with this one in terms of piping changes, in terms of base plate changes. Drops right in. 24% energy reduction that we saw here, about $201,000 in annual savings, 1,117 metric tons of CO2 reduction annually. So that's just one flow loop. Generally speaking, quick to market how you can install this. Granted, there's a lead time associated with pumps, but it's not a 10-year project, right? 15% 20-year IRR, which was our minimum goal associated with energy type projects with this end user. However, the ability to have redundancy in the system, go back to 1 out of 2 operation, is by and large more important to them than the IRR percentage, right? It almost sells itself. It's what they wanted, and we were able to deliver it to them with savings. Okay, I think this is the last one, and I like this one because it gets a little bit out of the only the energy optimization aspect of the system, right? This starts getting into reliability, which is it is a if you remember those kind of 4 main pillars, 5th one being sustainability. Reliability is a huge thing here. So these are asphalt bottoms pumps coming off of a vac tower, 700 degrees, really horrible service, right? Asphalt pumps. 1 out of 2 operation, 700 horsepower drivers, 2 parallel control valve branches, bypass line back to suction, generally closed. They opened it from time to time, but we kind of pared down the analysis to exclude that. These are Flowserve 6HUD25 two-stage BB2 pumps. I have here about $500K in annual maintenance costs. They were spending, we looked at 6 years of failure data. 500 was on kind of the low side of annual spend on mechanical seals here. Their mean time between failure was 3 months on these. It was just, they were beating these pumps and these seals left and right. Really, it's a hard service, number one, but they're operating these pumps just real bad, and we'll get into that here in a minute. So, start at the valves. Analysis performed with discharge pressure. There's a lot of pressure drop that's happening in this system, specifically across these first set of exchangers. We have pressure here, and we have pressure here. During prolonged runtime, but they were getting like 200 PSIG drop across these first set of exchangers. There's a whole nother discussion around how that can be optimized that needs to be had, and they're probably actively looking at, but they weren't willing to reduce any pressure in the system because of this. It's just, there's a lot of drop across those valves, or sorry, across those exchangers. We needed to maintain the margin that we had. So one thing here, this downstream, this FV24004, we didn't have a downstream pressure. This is one of those assumptions that we can make and use, equations and known parameters to calculate. If we know what valve is there, we know what CV is in. If we know that, we know how to calculate a CV. The CV calculation associated with that is flow, delta P, P1 versus P2, P1 minus P2 rather, specific gravity, valve percentage. We know all those things, we can calculate a downstream pressure. Now, that's a pretty decent assumption. There are some inaccuracies associated with that calculation, specifically on nonlinear parts of the CV curve. This valve was closed pretty, I think it was 20 to 30%. So at the lower flow rates, when you're on a nonlinear portion of that CV curve, you have a lot of error that's associated with that. And that's where you can see this, this flare out quite a bit. It's a phenomenon that I see happening a lot. I've talked to multiple valve people, and we have some ongoing discussions around the inaccuracies there. What we did was, if you can see that little red dot, we went and did a field survey. We went and took a pressure at a known valve percentage that was on that low side, plotted it, boom, plotted right, kind of in the thick of that cloud. Gave us some confidence there. We talked with the end user there. They gained confidence around it. We moved forward. Those are those conditions of service calls type conversations that happen that are super important. Okay, so no pressure reducing the system without major overhaul or redesign of the exchanger system. So, as I mentioned, horrible selection in pumps for one reason or another. A couple of things compounding here. They're oversized pumps, number one. Number two, they were in the past recirculating back to this vac tower. That has changed and isn't really required now. They made some optimizations so their vac tower can't recirc. So they're operating at roughly 25% BEP. This is 26% efficiency on those pumps. The seals are not meant to run at conditions like that. That's one of the factors that's associated with seal failures. The motor is really unloaded. There's some ability to increase efficiency not only through the pump but through the motor if we can get to an optimized condition of service. Future rate increase was considered. They've kind of given us an increase that could happen in the next 2 years to hit, so we just designed to that, right? If there's a pressure reduction that can happen, which in this case there wasn't, we just designed to the similar pressures that they're seeing at that max flow rates. Now, what does that do to overall brake horsepower consumption? I've been like droning on about decreasing brake horsepower consumption, and you do that by decreasing flow, decreasing pressure. Well, in this one, we're not decreasing pressure, and we're increasing flow. We are increasing efficiency, but if you remember me saying that the efficiency changes have less of an impact on brake horsepower. So, contrary to what I do on a daily basis, we're actually not saving energy here. There's actually, in the future, there will be some increased energy consumption, right, associated with the more flow that's happening. However, we're optimizing the system to that. right? So we're putting in place a recommendation that gives them the most efficient pump. We're have a huge focus on increasing mean time between failure. That was the main driver on this, right? They're spending upwards of $1 million a year on seals. Reduce that, get rid of that, and I mean, the project stands on its own. So, let's see. Already talked about seal mean time between failure at 3 months. The other option, or the other issue, they had a Plan 54 on this. They had no Plan 32, which you don't necessarily need a Plan 32, but the standby pump, if they fail to seal on the operating pump, the standby pump's secondary seal is just sitting there with, and its faces are coking. There's no 32 that's providing flush into that internal seal, or to that secondary seal, so it's starting, immediately failing. And so they're just throwing seals at this thing left and right. One of the recommendations that comes out of this is adding a Plan 32 at the most minimal flow that we can, so we don't introduce, which we were going to use HVGO on this, into their coking system, things like that. There's some discussion around there. So recommendation is moving to a 4HED25 donor hydraulic. So how we're going to go about this is maintain the casing of the 6HED25, engineering a donor hydraulic, a low-flow hydraulic to fit into that same casing. There will be some changes to the volute volume in order to reduce the amount of flow that's going through that. What that does is brings BEP back, cuts your efficiency curve back. Maintains 1 out of 2 operation. And I guess the other point on that, there's no civil work whenever you do something like this, right? You're maintaining the same pump casing. Touch points all maintain. You're just changing the internals. 60 to 112% BEP operating envelope. It is a big operating envelope, but we're giving them the best case scenario in terms of BEP. The motor is going to be loaded properly, so we're increasing efficiency there. No civil work, new seal selection. We worked with our seal division to give them the best possible seal that we could for this service that we were very confident around and utilize in this service. Full transparency, these pumps have John Cranes in them right now. Like, I want those seals. I want my seals in there. I'm confident around my seals. Give us a shot. You're spending $1 million in seals with these other ones. We can do better. We can. So in the heat generation, we're going to update to include the Plan 32. That's going to do a few things. Not only is it going to remove some heat generation in the seal, it's also going to provide for that standby pump. It's going to provide flush to that secondary seal, right? To keep those seal faces nice and flushed out, keep coke from forming on them. If they need to start up that pump, it's going to be more reliable. We are confident that we can push their mean time between failure from 3 months to upwards to upwards of 18 months. We'll see how that rolls out, but we're confident that there can be a roughly $500K in annual cost savings there. All of that wrapped up into a 58% 20-year IRR, which in the project funnel generally looks pretty good, right? Especially when this is the top bad actor on their site. They're really excited about doing this, as are we. I feel like I've been talking a lot. That kind of takes us to the end there. Any questions on anything there?
Just a question in this optimization. Did you all take in consideration like vibration readings?
We do.
For the units, right?
Yeah, so to an extent, right? And I kind of mentioned it first. My background is systems and vibration analysis. I've done lots of vibration work. I'm a Cat 3 vibe analyst. I did a lot of warranty mitigation type work for Flowserve for many years. We do take into account vibration in validating or in looking at these assets. If you have high vibrations, there's a reason, right?
So you're Cat 2 certified?
Cat 3.
Cat 3.
Yes, sir. Why are you having high vibrations, right? That's a piece to the puzzle. It's detective work. Why is that happening? Is it operating back on the curve? Is it on a variable speed type asset and you're interacting with a natural frequency? How can we get away from that natural frequency? There's things we can do from an engineering aspect to move the critical frequencies in that system, right? So yes, if you're having vibration type issues, those are all of those things that come in together, just like the seal failures. It's not exactly what I do in Energy Advantage. However, my My drive is to give you the best possible pump that I can. Most efficient, longest lasting, quietest running, less headache to you. I'm trying to take the headache off you. What are your pain points? Give me those. If you have one that has high vibration, again, there's a reason. We can figure it out. And if I can't figure it out from this analysis side, we have our solutions engineering division with guys that are all like Cat 3, Cat 4 type guys that can go out and do it. Very confident in those guys. Because I was once one of them. That's what I did for 7 years in Flowserve, was travel to sites, look at pumps, figure out why they're hydraulically wrong or what's wrong with them, from a vibration perspective, what's wrong with them. So yeah, we do take that into account. Long answer, I apologize, but yes, in short aspect.
Most of these pumps are what, horizontal or vertical?
So the vast majority of what we deal with is horizontal. We do deal with vertical pumps. Yeah. Vertical pumps, when you get, they have like their niches where they're more prevalent, right? Like if you walk into a refinery, I kind of know where all the vertical pumps are going to be. Like lots of circ water pumps happening there, pumps that really need more MPSH than you can provide them. Dig a hole and make a long pump and put it in it, right? Things like that. So we are pump type, pump OEM agnostic. It doesn't matter if it's a vertical. It doesn't matter if it's a Gould's. We can work on them. We can look at them. I'm right now I'm in the middle of a project at a geothermal plant up in Northern California. It's the largest geothermal plant in the world. And we're looking at condensate pumps that are oversized. Those geothermal plants they were designed 100 megawatt apiece. There's 14 different units, all situated on the fault, pulling steam directly out of the earth, pushing it across a turbine, and then gravity feeding it back. But those condensate pumps were never optimized in any way. Re-rated turbines, didn't touch those. So they're vertical can, and we're looking at them right now. So.
When you're done, you work on deep well pumps like 1,500 to 2,000 feet. Submersible pumps?
I have not. I'm not saying we can't. It's not things that I've looked at in my current role. But so a good friend of mine, Jim Rosendahl, he's an old man. He worked the test stands for United for like lots of years. You can look at pull United pumps and still have his name on them. He used to tell me, he was kind of a mentor of mine. He used to tell me a pump's a pump. Granted, that's a different service.
I work in the water company.
Yeah.
And we have 412 water wells.
Sure.
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 And these wells, they run 24 hours.
Mhm.
But we have to do maintenance work annually on all of them.
Sure.
Some of them fail after 6 months of operation.
Do you know why?
Right? Yeah, well, we did the whole analysis and study and everything. Right? It's a various combination of factors.
Sure.
Right? But one of the main factors was that how you measure vibration from
Yeah.
a deep well pump.
Yeah.
Right? That is the challenge we're having because the failures are because of vibration.
Sure.
Right? Pumps vibrating because it's deep well, so you really can't see anything on top.
Right.
It's not like a vertical pump or horizontal pump.
Right.
Where you can put your hand on it and you can feel the vibration. Right?
Sure.
These well pumps, you could, it's only when it comes very critical and you feel like the flow is dropping off, that's the only way, right? Then we start to do maintenance
Sure.
pumps, right? But to measure the vibration levels on a weekly basis is a challenge for us.
Sure. And I don't want to oversimplify it, but they're not failing because of vibration. They're failing because of something that's causing vibration, right?
So
That's it.
and that's what because of the experience we find out,
Yeah.
right? But when it comes to new wells
Mm-hmm.
that are just drilled and it's only 3 years old, and then they begin to fail, then that's a concern,
Sure.
you know?
Yeah, I mean, as long as, I'd say as long as there's ability to measure performance in terms of pressures and flows, understanding how it's interacting with the system, I mean, I'd say yes, in some degree, we can work on those. I don't know that it'll specifically be energy advantage. To be perfectly honest, it sounds like that's more of our solutions engineering division. I mentioned those guys, they're high-level vibration guys, have the instrumentation to go out there and fill in gaps in data that if you don't have in terms of pressures and flows and things like that. They are well-versed in finding solutions to issues like that. So I'd love to look at them. It almost sounds like the first pass is probably our solutions engineering division, which we have access to. I mean, as a solution engineer, I came to Trinidad and worked in different facilities doing similar things to that. Not on those pumps, but I'd be interested in looking at them. But.
But we use a lot of your Flowserve products.
Sure.
We use your pumps. Those pumps are run by 800 horsepower units.
Okay.
At the Caribbean water plant. I think this company did some work on it. And they do work every year on those pumps.
Sure.
Not just the Flowserve, they have transfer, they have all kind of pumps.
Yeah.
They do work on. And we buy valves, Flowserve valves, we buy for tapping equipment.
Sure.
Seals and stuff like that. So a lot of
Yeah.
Flowserve products.
Yeah.
We have been invested in over 50 years.
Sure, and we appreciate that. I'll be the first to say thank you. Let us be another tool in your toolbox, right? Whether it's solutions, whether it's energy advantage, let us be a tool for you. It's what we're here for. These guys have access to those teams. They know how to set those teams up. Let us be a tool. I know we're probably bumping up against time. No, nobody's kicked us out yet, though, so hurrah for that. Any more questions? Cool. Well, thank you for coming. Thanks for taking the time. Thanks for the questions. Hopefully we can continue the relationship we have with y'all. Okay. Sure.